In this workshop, we are going to solve the CFD analysis of a flow around circular cylinder at Reynolds number is equal to 150. And you can see that we have the excellent data and for drag coefficient and extra hole number. And we have compared with two meshes. Also, I will show you the third mesh as well, the fine mesh. And you can see that how the data is matching with the given data from some experiments. Okay, so what you will learn in this course, the number one point is that how to set up the transient case in fluent, like to decide about the boundary conditions, the flow properties, the material properties. And then the most important thing for any transient case is the time steps, number of time steps, and then for how much time we should be making the simulation. And also you will learn that how to set up the monitors for the transient case so that we can get the important information from these monitors. So these monitors will not only tell you about the convergence, but also they will give you the very important information about the convergence of the transient data and other important data from that case. So at the end of this course, basically you should be able to find out the drag and lift coefficients for transient case and extra hole number, animations, and contour and vector plots. Okay, in this problem, basically we are taking the Reynolds number is equal to 150, and why? Because of this chart. So in this case, we are going to solve the flow around circular cylinder. Reynolds number is equal to 150, and beyond circular cylinder, you will see that the vortex street is being formed, and you will see the vortex shading is going in this way, going up and down. So this is the one vortex that is, so vortex is like this, and it is moving in this way. Okay, this is known as a von Karman vortex street, and this is a laminar vortex street because the flow remains laminar. So now, before I discuss about the data, I want to discuss about this graph. So when the Reynolds number is less than 5, I will discuss about the Reynolds number definition also. When Reynolds number is less than 5, this is a creeping flow, means that the flow is dominated by the viscosity, and therefore you don't see any structure of any vortex here. So no separation at all, and flow is fully attached on the complete cylinder from start to the end. Okay, then we have the when the Reynolds number is from 5 or 15 up to the 40, we have the stable vortices in the wake. So there is a pair of counter rotating vortices, and they are stable. They are stable in the time, and they are stable in the space as well. They don't move with the time, they don't move in the space. Okay. So the third is a case where Reynolds number is from 40 to 150. That is the limit of the case where we are solving here. So in this case, we will see that the flow will separate alternatively from the upper and the lower side, and that's the reason that it makes the vortex. And you will see that there is a laminar vortex, and it is changing direction from top to bottom alternatively. And then we have the Reynolds number that is from 150 to 3 to 10 power 5. Here we have the laminar flow up to separation point, and after that we have the turbulent wake. And then from this Reynolds number to 3.5 to 10 power 6, we have the transition of laminar boundary layer to turbulent at some point, and then you see some flow structures behind the cylinder. And when Reynolds number is greater than 3.5 10 power 6, we see the same case as the case we are solving here. But only difference is that here we have the laminar vortex, but here you will be having the turbulent vortex. And turbulent vortex is dominated by the multiple scales of the vorticity, means that vorticity will have the different sizes. And in the case of the laminar vorticity, there the vortex has the only one size. But in the turbulent case, the vortex will be of the different sizes. And I will discuss this thing that with the LES, we will be able to resolve all these vortices. But with U-RANS, that is the unsteady Reynolds average equations, we will only be able to solve the one single vortex state. Okay, so this is the reason that we selected this Reynolds number for this case. Okay, so from these two references, the drag coefficient for this cylinder at Reynolds number is equal to 150 is 1.5 and the Stall number is 0.172. Okay, let me give you the definition for Reynolds number and then Stall number. The Reynolds number is the ratio of inertial forces to viscous forces. Means that if the inertial forces means that if the velocity is dominating, we will see that the Reynolds number is high. And when the viscous forces, like the viscosity is dominating, we will see the Reynolds number is low. So this is a ratio of these two forces. And if by definition, it's given as a density times velocity times any characteristic length. So this can be for anybody, this can be the front length, this can be the diameter for cylinder, this can be the hydraulic diameter for the internal flow in the cylinder. So this can be any dimension, but for circular cylinder, this is going to be the diameter of the cylinder, and then divided by the dynamic viscosity. So dynamic viscosity has the units of Pascal second, and also we can show them as kilogram per meter second. The second thing you might have seen in the Reynolds number definition is the mu divided by density. This is known as the kinematic viscosity. And this is known as the dynamic viscosity. So if you divide the viscosity by density, you can see the units would be like so. But after simplification, units for the kinematic viscosity are meter square second, and also we denote the kinematic viscosity by the scientist Stokes. So units are Stokes also, and the one stroke is equal to 0.0001 meter square per second. Okay, so this is about the Reynolds number, and then some definitions about the dynamic viscosity and kinematic viscosity. Now the next important number is the Stall number. That is an important topic of this whole exercise. So Stall number is basically the ratio of inertial forces versus inertial forces. But this is inertial forces due to the local acceleration, and this is the inertial forces due to the convective acceleration. So now let me explain what is the meaning of this thing. See, local acceleration means that this is given as dv by dt, the rate of change of velocity. Now this can happen because of the many reasons, but in local acceleration you will always see that some external force is always involved. For example, if you are seeing the car is accelerating, so it is because of the power from the engine. You can see that the flow is accelerating at the outlet of the pump. This is because of the input energy from the shaft, that is we are getting from the electrical source. So that shaft energy will rotate the impeller, and this will enhance the energy of the flow, and that will be seen as acceleration. This is known as a local acceleration, and it depends on the time. Second is the inertial forces due to the convective acceleration. So convective acceleration means that this is the du by dx or dy. So it means that when the velocity is accelerated, when flow is accelerated because of the change of the position. So what is meaning of this thing? So the flow still is a steady state, means that it's not changing with the time. So if you take example of nozzle, now in this case we are not providing any energy to the flow, so it is accelerating because of the shape of that particular body. So it is converting its pressure into velocity. So this is getting local acceleration. That's why we call that the velocity here. Let's say this is the u1, this is the u2, and distance between them is the dx. So definitely we'll see the velocity is enhanced here. So here in this case, u2 minus u1 divided by delta x is a positive quantity. And in the case of diffuser, you will see this quantity will be negative quantity because the velocity is decreasing. Okay. So And in simple definition, this Stall number is frequency times diameter. So if you're taking the cylinder here, so this is the diameter, and the frequency is the frequency of the vortex behind the cylinder, and the velocity is the incoming free stream velocity. This is uniform velocity, this is u, sometimes v, or sometimes we show it as a v infinity. Okay, so now let me give you idea that when we solve with the help of the laminar flow model, so what will happen? Basically, if you take a look here, if this is the cylinder, so this is the, when flow moves over the cylinder, this is the source of the energy. This is source of energy. So the geometry scale is like here is L is equal to D. So this is the geometry scale, but it will increases the flow energy, and then the flow energy will be changed into the different vortices, and then they will eventually will be dissipated, and then they will go and mix with the free stream velocity, free stream flow. So might be you will see that initially the vortex size is smaller, then it will get larger and larger. Okay, so then they will eventually dissipate, and they will be changing to, and at the same time, if you take a look on the turbulent flow, we might have observed then there are the multiple scales. So eventually this all energy will be dissipated, and they will be changed into the viscous dissipation. So eventually this will be changed in the form of the heat energy. So in the case of turbulent flow, we have a lot of vortices, a lot of vertical energy here. So to resolve them, basically we cannot solve them with the help of the U-Rens. So Rens is a steady state, and U-Rens is unsteady Reynolds average Navier equation. So if you go for turbulent flow, we are not solving turbulent flow. So for turbulent flow, the U-Rens will only resolve the single largest vortex in your flow. Okay, so this will solve the largest eddy in the problem. This is going to be like this one. And if you go with the LES is going to solve the majority of the eddies, but it will not solve the smaller eddies. But if you go with the direct numerical simulation, it will resolve all the eddies. So resolve means that we are solving, and model means that we are modeling with some equations. So basically, in the case of the U-Rens, we are modeling everything that is for the turbulent flow, but we are only solving the one major eddy. Okay, so now I think now you know about this difference. So that's why that largest eddy, because the largest eddy is basically dictating the flow, and from that largest eddy, basically we get its frequency, that how much times it is moving from the one space. So from that thing we get the frequency of that particular eddy, and this frequency is, the units of frequency are the 1 upon time, and from this frequency we can get the time period that this energy, this eddy is going through some cyclic process, means that it is like it is moving position in this way. So this can be some sort of the sine wave or cosine wave. So we can find out the time period of that particular wave that vortex is following, and the frequency is the 1 upon time period. So from frequency we can get the time period by making the time period as 1 upon f. This is the whole idea about solving this problem using the CFD. Okay, so now these are given conditions. The Reynolds number is 150, and we have assumed few values. So we assume the diameter is a 1 meter, velocity is a 1 meter per second, and density is 1 kilogram per meter cube. So why we are doing this thing? Because the Reynolds number should be matched. Now we can set any parameter in the Reynolds number as far as we are getting the Reynolds number same. So we can vary anything in the CFD like density, velocity, diameter, and viscosity. So now we have assumed 3 values. So now the 4th value should be calculated. So this is the viscosity. So we can solve viscosity as the rho Vd upon Reynolds number. So density is a 1, velocity is 1, diameter is a 1, divided by 150. So we get the viscosity as 0.006667. The domain size is set in this way. The diameter of the domain of the cylinder is 1 meter, and upstream distance is d1, that is 20 times d, which is equal to 20 meters, and downstream size is 45d, and this is equal to 45 into 1 is equal to 45 meters, and across the distance is 40d, that is the 20d on the upper side and 20d on the lower side. And this size basically I have taken after referring to many papers, and as we will see that there is a vortex state that is being formed on the downstream side, so it goes to the very large length. That's why I'm taking this distance to be very, very large. And we are going to create 3 meshes. One is a coarse, second is a medium, third is a fine. You can also go with the extra fine mesh that can be approximately 80,000 nodes. So this is the O grid inside, and then the shape type grid in the far stream. So in the rest of domain it's the H type, but in the closed vicinity of cylinder this is the O grid. And the minimum orthogonal quality is 0.75, that is close to the best. Okay, and as far as the domain boundaries are concerned, so the top and bottom, they are set as symmetry. And the inlet is a velocity inlet, outlet is a pressure outlet. At the inlet, we are going to provide the velocity that we have determined or given, assumed here, based on Reynolds number. So this is a 1 meter per second. At the outlet, this is going to be 0 Pascal. But 0 Pascal does not mean 0 Pascal. This is a gauge pressure, and operating pressure is defined separately in the fluent by default. So this becomes 101325. So same pressure is basically there on the inlet. So this is the atmospheric pressure is given on all boundaries. Okay, now the concept of time step. So we know that, but this thing can be different for different problems. But for this problem, because we know that there is a vortex straight beyond the circular cylinder. So basically, we are trying to resolve this flow. So now if there is a one wave, so how you will solve this thing? If you, this is a time period, that is time period of from the one position of the wave to second position of the similar position of the wave. This is known as a time period, and the frequency is that how many such peaks we can get in a that particular time. Okay, so if you want to resolve this complete thing over here, so if you make the one time step, so you will not see any ups and downs. So if you are here and if you jump from one point to second point like this, so you will only see this single particular velocity or the frequency over here. If you go here, you will see the only one thing here. So you cannot resolve the flow in a one time step for the this whole period. Okay, so we have to divide them into number of time steps. So we have divided into 20 time steps. We can divide into 40 time steps. So dividing means that we are advancing in the space. So in the space, for example, this is cylinder, this is the one vortex. Okay, so basically we are moving the flow in such a way that the flow is moving in the differential forms. Okay, so at this point this will solve this point, this will solve at this point, this point. So in this way we can solve this wave in the discrete fashion, not in the continuous fashion because it's a CFD, but in discrete fashion that we get the different points. And if you make the more points, means that you are basically approaching to the true shape of that particular curve or that particular frequency. So as we reduce the time steps, basically we are approaching to that continuous behavior of that particular thing. Okay, so this is the whole thing about that time, so total time will be equal to at least the 5 cycles. Initially we will allow the flow to establish itself. Then once the flow is periodic in nature, like it is repeating itself, so we will allow the flow to establish itself in the periodic nature, like it is following the some pattern. And after this is confirmed, then the last 5 cycles we will take the data and we will average out the particular data for drag coefficient, for lift coefficient. And to find out the frequency, basically we are going to apply the fast Fourier transform on the some parameter like the lift coefficient, or maybe we are going to set the velocity monitor at some point, and this is going to be the y velocity, because y velocity is not changing in normal uniform flow, but in the case of the vortex you will see that there is a y velocity as well. Okay, x velocity versus y velocity. So the change in y velocity is going to give you the idea about the largest frequency, dominant frequency in the flow. So that frequency we will find out from the application of the fast Fourier transform, and this is given in the inside the fluent. Okay, so now from here the question arises that we don't know about the frequency of the flow. So how to make the time step? So number one thing is that there is basically from the previous experiments we know this thing that the stall number is found out from those experiments. So we know this data. Okay. Second procedure would be that you will have to run this case for the many time steps and then see which is going to give you the particular frequency that is not changing with the time step. That will be like a time consuming process. It requires a lot of time, lot of efforts, but fortunately we have the data from some experiments. So we know that the stall number is equal to 0.172 for circular cylinder at Lorentz number is equal to 150, and you will find the stall number for different Lorentz number from the literature. So we can solve for the frequency. So this becomes stall number times velocity divided by diameter. So if you put the value of stall number and velocity and diameter, you get frequency as 0.172. Okay. So the time period is 1 upon frequency. So you get the time period for one vortex period equal to 5.8139 seconds. So if I assume that I'm going to resolve this particular vortex frequency by 20 time steps, so the time step would be equal to T upon N. This is 5.8139 divided by 20 is a 0.291. This is the time step if you are resolving this into the 20 time steps. In the case of 40 time steps, delta T would be equal to 5.8139 divided by 40. This is half of this value. Okay, so we are going to use these settings. This is the coupled pressure based laminar and incompressible flow, and second order schemes for all variables. This is very important. Otherwise, you will not see any vortex shedding. You will not see any vortex. So if you don't use the second order scheme for all variables, including velocity, continuity equation, you will not see this thing. And also for the time step. Okay. And the current number is we are going to set the maximum, but right now in the new fluent this value is no more relevant. Okay. So I will see this thing also. And we will use a second order implicit scheme for temporal resolution. Temporal means that this is the time step. Okay. Okay, so you have to set the time, the different monitors. These monitors will help you to find out the frequency using the FFD. Therefore, we are going to monitor at these 4 points, and 4 points because sometimes some location may not get that particular understeady flow. So that's why I use 4 points, and also I given the dimensions or locations for these 4 points: x1, x1, x2, x2, and the y is 0.5, 0.75 and 0. As far as the regular mountains are concerned, like the velocity and momentum equation, they are set to 10 power minus 15. Why? Because for laminar flow, the convergence rate is very high. So unlike the turbulence flow where the convergence may be limited to 10 power minus 4, for laminar flow, the convergence criteria may be we can get the residuals up to 10 power minus 15, and sometimes we can get them up to 10 power minus 20. So that's why I set them low. And then I will allow to run this case for maximum time steps so that I get the product flow. Once this is established, then I will stop. And usually speaking, the lift coefficient monitor is better indicator of dominant frequency. This is seen from experience. So that's why we will go with, in addition to these 4 points, we will go with the lift coefficient as well for getting the dominant frequency using FFT, fast Fourier transform. Okay. And also we are going to set up the water shedding animation in the beginning of simulation. And so with every time step, you will get this movie or clips. And then at the end of the simulation, you will convert these frames into animation file. Okay, this is about the like the drag and lift coefficients, how to monitor them, and so you have to set them from the monitors. And in the new Fluent, this is from the report definition. So I will tell you how to do this thing. And this is like the vortex average of different points. Okay, so as far as the solution initialization is concerned, so the one way is that we can run them for 600 iterations until we get the transient behavior. Okay, and after that, this is like not iteration but time steps. And then we use record save data for next 2000 time steps. So basically, if you are making the 40 time steps per cycle, so this means that you are recording them 50 cycles. You are recording data for 50 cycles. So 50 cycles may be too much. You can limit them to the maybe up to 10 cycles or 5 cycles. Okay. And I'm also going to define I'm also going to give you the steps to make the geometry and meshing in ICM CFD. Okay, this is what you are going to get. So initially, the solution may show you the steady state behavior, but once the water shedding start to develop at the downstream side of the cylinder, you will see these transient data. Okay, these are fluctuations in your parameter, like this is the velocity. So once they stabilize, means that the behavior is periodic, it is repeating itself. After that, we will record data for averaging data, for example, drag and lift coefficients, and also for FFT, we will use that particular data set. Okay, and one more thing is that you know that the lift coefficient basically for symmetric body average value would be 0. So CL average would be equal to 0, because this is alternately changing around the 0 value. So normally speaking, when they quote the lift coefficient for symmetric bodies, they use the root mean square value. So root mean square values means that we will have to square every value, like CL at 1 time step 1, time step 2, time step 3. Okay, and if there are 3 values, then divide by 3 and then take the square root. This is how we are going to get the some positive quantity, and definitely this quantity will be same for same Reynolds number if you do simulation by yourself or anybody else is doing simulation at some other place. So RMS is the best criteria for lift coefficient if you want to compare lift coefficient. Okay, and here you can see the CD is plotted for different time steps. This is the flow time, This is the time step. So basically we get the average values for the any parameter, like here is a coefficient of drag. So when we average them in the Excel, so average means that for every time step, if you sum up the values then divided by the number of time steps, you would be getting the average quantity of that particular parameter, like here is a CD. So from that way, we got the drag coefficient experimentally is a 1.5, with the coarse mesh is a 1.313, and for medium is a 1.319. This is for 20 time steps, and stall number is 0.172 from experiments, and from coarse mesh and medium mesh 0.1735, 0.1757, and this is again for 20 time steps. For 40 time steps, the values are little bit closer. Okay, so these are some water shedding. You can see the plots, and some animation also are given in the over here. So this is the behavior of the velocity vectors. You can see this is a zoomed view. And also I'm going to, you have seen one thing, that for circular cylinder, people show the data like CP, coefficient of pressure versus angle theta. So starting with a 0, 45, 90, so maybe you can say it's a 180 and 360. So CP may be changing in this way. This is just example. So I will also tell you that the method that how to plot the CD, the CP along the different angular positions of circular cylinder. Okay, so now let's start with geometry, then meshing, and then set up the problem.